pleasure to introduce Professor T.W.B. Clyne from Cambridge University. Professor Clyne is the Emeritus Professor at Department of Material Science and Engineering, Cambridge University, UK. His research interests center on the thermomechanics of composites and coatings, particularly processing, numerical modeling, and fine-scale mechanical interrogation. He has authored more than 300 papers and 2 textbooks on composites and 10 educational software packages. He has been a sole supervisor for more than 80 PhD students in Cambridge University, and he has delivered 50 invited keynote talks. He was the president of Federation of European Material Societies, and he is the director of globally accessed educational material science website also, which is very useful for all students of materials community. He has been awarded the Griffith Medal, a premier prize of the Institute of Materials. He has been elected fellow of the Royal Academy of Engineering as well as Helmholtz International Fellow in 2014. Thank you, Professor Clyne, for joining us today. Now, let me introduce Dr. Jimmy Campbell. He is the Chief Engineer at Plastometrex Limited in Cambridge. He completed his PhD degree in Department of Material Science and Metallurgy in Cambridge University. In 2018, he has focused on developing the novel approaches to measuring the mechanical properties of metals via indentation experiments. He has also co-authored about 15 journal papers and textbooks which are focused mainly on testing the plastic deformation of metals. In Plastometrex Limited, Dr. Jimmy has led the design and manufacture of the indentation plastometer, a benchtop indenter with integrated profilometer. The machine, with its automated workflow, creates an indent and scans the residual shape. So he will be presenting with Professor Clyne today on obtaining the metal plasticity and failure characteristics via iterative FEM modeling of indentation, the PIP methodology. Professor Clyne and Dr. Jimmy, over to you.
Well, thank you, AJ. That's very kind. So, as you say, we're going to try and give some kind of introduction today to a fairly novel methodology, although it's based on well-established principles. And as you also mentioned, we'll do this as a double act. I'll give a talk of about 15 or 20 minutes myself, and then I'll pass over to Jimmy to do the second half. And we'll take questions at the end of both of those, if that's okay, because we're covering essentially the same kind of area. So it is based on work that's been done in the university over the past couple of decades, really. But what's brought it into focus is that there is this startup company called Plastometrex, which is now marketing some products, and you'll hear a bit about the actual machine itself towards the end of the talk, although you can see a picture of it there. So let me just give you a introduction first to what is actually in the talk. So this is the structure. I'm going to start off by just giving some background really to the concept involved. We call it PIP. It's based on making indents, measuring the indent profile, and then doing a repetitive, iterative FEM simulation of the process in order to converge on the best fit set of plasticity parameters. What we're trying to establish is the stress strain curve of the material. And although it does involve a lot of FE simulation, the whole thing takes place rather quickly. So, it's a rather tractable tool if you have an integrated system where you can make the load, create the indent, measure the profile, and then do the software, the iterative FE. So here's the basic idea pictorially. You start by making an indent to a prescribed load using a spherical indenter, a relatively large spherical indenter. You measure the profile rather carefully, and then you need some kind of constitutive law to describe the plasticity. We use the Voce equation. There are alternatives, but you need to be able to simulate the plasticity. So you carry out FEM simulation of the test. You look at the predicted profile, you compare it with the experimental one, and you evaluate the difference between them, the error, this S parameter. And the better the fit, the smaller the value of S. So you decide whether you've converged sufficiently. If not, you repeatedly carry out the FEM simulation with altered values of these plasticity parameters until you get the best fit, and then that's given you the plasticity law. From that point, you can do all sorts of things, simulating other situations, etc. So here's the kind of thing that goes on during that process. This is actually showing you how that misfit parameter, that S value, is changing with repeated iterations. This is a log scale, so down here we're down to very low values, and we're aiming to get a value somewhere around here, 10 to the minus 4 or so. So these are the corresponding values of the plasticity parameters being iteratively changed until eventually we settle down to something which is the best fit. And all that happens rather quickly during an automated process. So just emphasizing again the sequence, you create the indent using a large spherical indenter. You measure the profile. Here's some different profiles for different applied loads. If you're interested, you can start focusing on looking at the microstructure around the indents. This is showing these persistent slip bands in individual grains, so you can get some feel for what's actually going on inside the material. But the key procedure is then to repeatedly simulate the indentation process, and as I say, get the best fit between the measured and modeled profile, and then that gives you the true stress strain curve. That's what we're trying to obtain. Once you've got that, you can simulate all sorts of things, including the tensile test, for example. So you could put those true stress strain parameters into another model, and you can predict how a tensile test would proceed, including simulation of the necking, etc. Or you could do all sorts of other things if you wanted to. So that's it really, but there's a lot of subtleties in this to get things right. And of course, you do need to understand the difference between true and nominal stress strain fields. So this is the outcome of FE simulation of a tensile test, a particular one. This is the true stress, true strain relationship for plastic deformation. And you can simulate when necking will start. In this particular case, it's here at about 20% strain. Up to that point, the stress and strain fields are uniform. Beyond that, obviously you get a lot of inhomogeneity as the neck starts to develop. And the true strain in the neck is being monitored here, and then it's fracturing at a certain point, which is actually often something you can predict in terms of a critical value of the true strain in the neck being reached, in this case about 80%. So that's the kind of thing you can do. Now, the bottom line is what actually happens if you take an unknown material, you make an indent, you carry out this process, and you end up with a nominal stress against nominal strain curve, which you can compare with a conventionally obtained one from a tensile test. So this is just a couple of examples. These are actually both copper samples. One of them as received, as extruded, so quite a high yield stress, not much work hardening. On the other hand, the same material after annealing, gets much softer, much lower yield stress, although it then work hardens a lot. And as you can see, you're getting pretty good agreement between the conventionally obtained curves and the ones just from indentation, followed by this iterative FE procedure. So that's the basic idea, and it does work, so to speak. But there are a number of issues, and you need to be confident you're capturing what goes on rather accurately. Another thing you can compare, if you want to, is the way the neck develops. Obviously, you can do this to some extent via the stress strain curve, but also you can look at the shape of the neck. So this is for a couple of different materials. One is copper, another one is aluminium alloy. Different stress strain curves, of course, different true stress, true strain curves. So when you do the simulation, you can compare not only the stress strain curve that you measure, but also the neck shape. And you can monitor how the strains are developing. These are the von Mises strains as a function of position here, obviously reaching a high value at the neck itself. This is just before rupture, and the level of true strain reached in the neck commonly reaches something like 100% or something like that. What else? Well, there's a number of important features of the process if you're going to get this right. And one of them is the scale. And this is an important issue. What scale should you do this on? If you make very small indents, you'll probably be in single grains and you'll get very different behavior. Because if you want to capture the bulk response of the material, you do need to deform a relatively large assembly of grains, what you might call a many grain volume. And the reason for that is that the way the bulk behaves depends on a number of things. It depends on things like grain size, texture, the structure of the grain boundaries, because that affects the ease of rotation and sliding at grain boundaries. And of course, the usual things that you might expect anyway, dislocation density, precipitates, etc., etc. But it is important to deform a many grained volume. And what that translates into, if you recognize that the grain size could be anything up to 0.5 millimeter or even more, but this would be a typical range up to, say, 500 microns. That means you need an indent diameter, which is at least around 1 millimeter, and probably an indenter radius of around 1 millimeter as well. One of the things this brings in is that you need a reasonably large load, depending on the hardness of the material, of course, but you're probably going to want something in the kilonewton range in order to create this indent. It's still relatively small on a macroscopic scale, but it's not small in the sense of being what you might call nano indentation, which is much, much finer. And nano indenters have load capabilities down in the Newton range, if that. They can't be used for this kind of thing. So you need a special or a suitable loading frame that can generate loads in this range. So that's an important point to note, scale. There's other issues. One of them is what kind of plastic strain do you create during the process? You obviously need to create a relatively large range of plastic strain. If you're trying to capture how the material responds during a typical tensile test or something like that, you need to be going up to tens of percent typically. If you've only created plastic strains of a few percent, you're not going to capture the response over the right sort of range. Now, the plastic strain range depends on a lot of things, but obviously it depends on how deeply you're going relative to the indenter radius. So both of these are going to a depth of, well, a few hundred microns, and they're different materials, so that affects the strain range you get. This is a material not exhibiting much work hardening, so you get quite high strains, quite localized. You also get a big pileup. If you have a material with more work hardening, then the plastic strain gets diffused over a larger region and there's a bit less pile up. But in both cases, you can see that we're generating strains up into at least several tens of %. And that's the kind of thing you need to do. You need to go down to a reasonable fraction of the indenter radius. Perhaps 20% would be a typical depth to go to generate the right sort of strains. So this all ties in with the numbers I was giving earlier. If the indenter radius is about a millimeter, you want to go down to, say, 200 microns depth. And in fact, the way we run this procedure is that we increase the load until the depth reaches a suitable kind of range, something like that, 20% of the indenter radius. So those are important issues. If you want to go deeper into this, you could do something like this. You could say, during the FE simulation, I can note what fraction of the total plastic work is done in different ranges of plastic strain. Obviously, the deeper you go, the more you're going to get work done at slightly higher strains. But you can convert this kind of modeling to this. You can find out the average, the weighted average plastic strain that's been generated as a function of how deep you go. So this again is for 1 millimeter indenter radius. So this is 20% penetration. And as you can see, if you go to that kind of depth, you're generating average plastic strains that are affecting the behavior up around 10 or 15%. And that should be suitable for capturing the behavior overall. Do need to go reasonably deep. So say 20% is a typical value we aim for. Okay, I think at that point, I'll pass over to my colleague, Dr. Campbell, who's going to give you some more information about some of the kind of issues that really turn out to be important in some cases. Things like the material being anisotropic or there being residual stresses, etc. present. So over to you, Jimmy.
Thanks, Bill. So, as Bill said, there's two issues we're going to look at. The first one being plastic anisotropy, and the second, residual stress, which may occur in materials that we're going to conduct our indentation experiments on. So, if we look at anisotropy first, one area where we might see significant plastic anisotropy is in additively manufactured metals. This example here is of a nickel-based superalloy, and we can see here on the left-hand side EBSD scans from two different orientations. So this one in the XY plane, showing a relatively equiaxed grain structure, and this one in the XZ plane, showing that there's clearly been directional growth occurring along the build direction. So it's clear in this case that we've got a strong 100 texture parallel to the build direction, which is what you would expect in nickel-based superalloy. What we can see on the right-hand side here is that this texture leads to quite significant anisotropy between the horizontal and vertical direction. So the horizontal is the in-plane direction, and the vertical is the build direction. What we can also see, if we zoom in on the elastic region, is that the material is stiffer in the transverse direction than it is in the build direction, and that is because of the 100 texture. So it is less stiff in the 100 direction. So what happens when we indent this material? Well, on the left-hand side, we can see an SEM micrograph of the indent after indenting in the XY plane. And in this case, the indent is radially symmetric. So in all directions, all of them being transverse directions, we produce the same scan. So there is no difference depending on which orientation we take our profilometry measurements. However, if we indent in the XZ plane, what we can see here is that the indent, when viewed under the SEM, it looks almost elongated in one direction. So in the growth direction, we can see that the indent looks almost wider than in the transverse direction. And that is because of the different pileup we can see on the right-hand side that occurs in the different directions. So in the transverse direction, indicated on the graph as the 0 degree scan, we have less pileup. And in the 90 degree scan, so in the growth direction, we have much more pileup. And what that indicates to us that in the transverse direction, the material is more resistant to plastic deformation, i.e. it is harder, which is the same as that we saw in the nominal stress strain plots previously. So what can we do with this information? Well, if we take the radially symmetric indent, the prediction from pit testing is shown on the plot here. And we can see that fairly good agreement is achieved. We would expect, on the basis that indentation is a multi-axial procedure, so that deformation will occur in all directions effectively, unlike in a uniaxial test where we're only testing in a single direction. And we see that the agreement comes out here closer to the transverse direction, which is what may be expected given that there are more transverse than axial directions when indenting in this plane. At the moment, we have no capability for quantifying anisotropy from an anisotropic indent, but that is an area of active research for us here at Plastometrex. And at least the profiles do allow us to assess that there is anisotropy present, and it reveals some of its nature, i.e. in which direction is it going to be harder or softer. Okay, so if we move on to residual stresses. So the way that we investigated residual stress was using the rig shown on the left-hand side. So it's quite difficult to generate residual stresses of a known or very accurate value. And so how we decided to do it was to apply the load to the sample. So you can see that we've got a cruciform shaped sample, and these 2 points here and here are fixed. And in these ones here, we apply a load through the loading nut and measure effectively the applied load through this strain gauge here. So in 2 different directions, we can pull on these loading nuts, generating a stress in the material, and we hold that constant as we perform the indentation. So previous papers had stated that they used the applied load from this kind of setup divided by the area of the sample in the cross section here to give you the residual stress in the center of the cruciform. Unfortunately, that's not quite right. There are 2 things that you have to consider as well. The first of all are the Poisson effects from the contraction that change that area. That's a relatively small effect compared to the effect of having an effectively large cross-sectional area in these regions just due to the curvature that you have to have on the arms. Now, what that leads to, if we simulate this relatively simple case, is that the stress in the arms here in the X direction and here in the Y direction, if we apply the same load in both directions, we'll see symmetric effects in the X and Y stresses. But you can see that the stress is quite a lot higher in the arm than it is in the center. Now, this leads to the von Mises stress looking not quite as uniform as you might expect initially, but it does result in this central region here having a relatively constant residual stress. So we're looking at the equal biaxial case, and in this region, the von Mises and indeed the X and Y components of that are relatively constant. So we can see here the results of the indentation experiments for different applied residual stresses. So this is in the case of this is written just as applied loads. And we can see here at the applied indentation load of 1/4 of a kilonewton that there is some differences between the indentation experiments. When we increase that load to a kilonewton and therefore go a lot deeper, we can see that the effect of the residual stress is much weaker. So there is not that much separation between almost all of the cases there. So what we can then do is take those indents. We know the plasticity parameters because we can take that from our indentation experiment performed on a sample with no residual stress. So we know the plasticity properties, we put those into our FE model, and we then vary the residual stress, and we can then calculate the misfit parameter for each of those values of residual stress. And what we can see here is that we do get a minimum and therefore a best fit for each different value. And you can see that each of these does have a minimum rising on either side. And we can see that the correlation at the lower depth is okay. So here, the blue one is actually a residual stress of 115 megapascals. That's quite close. There's a bit, it's a bit less well defined in this region, but as we go negative, we have -60 and -30 and -106. But my apologies. -106 would actually, we're predicting residual stress of almost -200 there. And then we can see for the deeper indents, we're getting much less sensitivity to the residual stress. So as we might have expected, looking at those indentation profiles, actually there is very little sensitivity at those depths. And this is summarized in this plot here, which shows the inferred residual stress against the actual residual stress. And we can see that at low penetrations, we're getting a reasonable agreement in terms of at least the correlation, but there's a lot of scatter around that. And then at the higher depth, we're getting very poor sensitivity to the residual stress. So one reason that you can look at to sort of explain this is that after a reasonable penetration, the radial stress fields look quite similar, whether there is no prior residual stress or a tensile residual stress here of 115 megapascals. So you can see that the field is dominated by the plasticity that has occurred. And that may help to explain why we don't see very good sensitivity to the residual stress. So what's the outcome of this if we just ignore residual stress and only try and infer the plasticity parameters? So in our model, we keep the residual stress set to 0, and then we try and infer with different sets of indents where residual stress had been present. So we can see at the low loads, the effect on the yield stress so the yield stress in this case is 200. The effect on the yield stress is reasonable at these lower depths. So we can see it drops down to 100 or up to 250 when we have residual stresses, which are 180 megapascals, so quite high in this case. As for the UTS, which should be around 260, we can see that there's a very large spread, and this value can go up quite significantly. So that's all for the shallow set of indents. In the deep indents, the effect is much less, as we might have expected. The effect is much less marked. So the compressive residual stresses will have a very small effect on the yield stress, and indeed the UTS at large penetrations. And the tensile residual stresses we can see have more of an effect on the yield stress, but almost no effect again on the UTS. So again, for relatively deep penetration, we can see that the effect of the residual stress is much less significant than at low penetrations. Okay, so finally, I'd just like to introduce you to the Plastometrex indentation plastometer. You can see here the key components are labeled. So we have an indenter with an LVDT, base plate, and an integrated profilometer. And I'd just very quickly like to show you an introductory video from the plastometer.
Welcome to Plastometrex. This is one of our indentation plastometers. And today, I'm going to show you just how simple the workflow is. Here, we have some aluminium plate, and for sample preparation, we've done a quick surface grind, and we've ensured that we've got a flat surface for indentation. To run a test, place the sample underneath the indenter head. Once you click start, the indenter head will come down, and the LVDT will come into contact with the sample surface, and the indenter head will pause. This allows you to make any fine adjustment to the position of your sample for the test. Once that's complete, everything from this point on is automated. The indenter comes down and touches on the sample surface and then begins to indent. If we look in our Corsica software, we can see the load displacement plotted as it is being acquired. Once the indenter has reached the appropriate load, it then unloads. The profilometer now comes across. The sequence the profilometer follows will be that it touches down on the sample surface, it then moves to within the indent and finds the center of the indent. It then moves back outside the indent and performs a scan straight through the center of the indent. Now we move into SEMPID, which will convert our residual indent profile into stress strain data. The straight into the software, and the user must then specify the material. This is important as it defines the stiffness which will be used in the calculation. Here we've indented aluminium, so I will select that as my material and perform the analysis. This will typically take around 10 seconds. Now that the calculation is completed, we can see here we are using the Voce plasticity equation, and underneath are the parameters that SEMPID has calculated in that equation for our stress strain data. On the plot, the dotted line shows this plotted as a true stress, true strain relationship, and the solid line shows that true stress, true strain relationship converted to a tensile nominal stress strain. This also allows the calculation of the UTS, or ultimate tensile strength, which here occurs at approximately 10%.
Okay, so it's just a short introduction video showing you a bit about the workflow. So in summary, we've looked at inverse FE modeling to infer the stress strain properties of metals. It's a transparent process. However, for it to be reliable and accurate, we've got to satisfy several conditions. First, as Bill outlined, is the scale. To ensure that the bulk characteristics are captured rather than just those in a single grain where the properties are highly anisotropic. And we don't actually capture all of the properties, such as the influence of grain boundaries. We must ensure that the diameter is large enough, typically of the order of a few millimeters, to make sure all of the microstructural features are captured. Spherical indenters are typically the best ones because they don't have any issues such as sharp corners, so the modeling, there's no problems with the modeling. And the residual indent profile is a much more sensitive outcome to the properties than the typically used load displacement plot. To characterize plasticity over a useful range, we've got to probe relatively deeply, around 20% of the radius, which means if you're going to use a millimeter-sized sphere, you need loads in the kilonewton range. So We then had a look at anisotropy, noting that indentation is multi-directional, so we get a direction averaged response. And we looked at the case of a nickel-based superalloy. Residual stress can affect the progress, but the sensitivity is low. This is especially true for larger penetrations, although it can have some effect at lower penetrations. And finally, we just had a quick look at the Plastometrex indentation plastometer, which will automate all of this for you and predict stress strain properties from indentation within 2.5 minutes. So I'd like to thank you all for tuning in today, and we'll be happy to take some questions.
Thank you so much, Professor Clyne and Dr. Jimmy. Now, I request all the participants to, if they have any questions, they can ask. We have Professor Nikhil Gupta and Professor Mohanty also there. If they have any specific questions, they can also discuss.
Hello.
Yeah.
Yeah. So somewhere in the slide you have shown that using EBSD measurement, you have shown the two cross sections, basically two planes of the additively manufactured nickel-based superalloy, and then we are calling it as some kind of texture is present 101, I guess. Yeah. Here only. And then when we are seeing the residual indents, and that time we are comparing the shape of those indents. So that shape is coming because of some crystallographic texture, or is it just the grain morphology which is resulting in this type of shape change?
I think you're asking whether it's the shape anisotropy of the grains or the texture that's causing the effect. Is that what you mean?
Yeah, crystallographic texture. Yes, sir.
Yeah,
Yes.
well, I think, I mean, we're just seeing the outcome, but I would expect it would be the texture that would have the strongest effect. I mean, the shape of the grains is relevant, but it's probably more dependent on exactly
because on one plane we are seeing very elongated grains, and on the other side we are seeing more of equiaxed grains. So is it just the effect of grain shape, or some
well, as I say, I mean,
texture?
Both could be contributing, but I think it's the texture probably that's the most important. You see, what's happening here is that obviously assemblies of grains are deforming in a cooperative way. If there is no texture and the grains are equiaxed, then obviously you'd expect it to be isotropic, to deform in a similar way, no matter which direction you loaded it in. But if it is textured and if it has shape anisotropy, there will be some differences. And here you're clearly seeing that it's harder in transverse directions. So
yes.
I think the answer to your question is I suspect it's the texture that's the more important of the two.
Actually, we have seen some papers in the Journal of Additive Manufacturing on SS316, basically the steel, and there they have shown that because of the shorter slip path, this anisotropy comes in the bulk samples, like we are seeing here also. And I suspect that it may be because of grain shape also, like in the TI64 and SS316 people have reported.
Yeah, I mean, you're absolutely right. And unless you do some very detailed modeling, it's quite difficult to separate the two. Certainly, the texture is quite strong. You can see that here just from these EBSD. I think there's a factor of about 4 from randomness in terms of the bias of 100 directions being aligned along the growth direction. So it's quite a strong texture, quite a simple one actually, but it's not simple to predict how that will plastically deform. You would need to do
some kind of crystal plasticity simulations, maybe.
Yes, it can be done, I'm sure. But all we're seeing is the net outcome here. And you're quite right, it could be getting influenced by both shape, anisotropy, and texture. Yeah.
Thank you, sir. And when we are simulating this tensile test using the Bose parameters obtained using the iterative FEM simulations, then how are we considering the effect of voids in predicting the necking?
The effect of voids, you said, did you?
Yeah.
Jimmy, do you want to take that?
Yeah. So we're not considering the effect of voids in the onset of necking. So if we look at this plot here, you can see that the nominal stress builds up to the maximum at around sort of just under 1100, and then the neck just begins to form, and that is just a geometrical effect, and indeed was predicted by Considere a long time ago. So in terms of the beginning of the formation of the neck, that is, as I say, it's a geometrical thing. You can predict it both from FE or just from converting the Voce equation in its true form into the nominal form, and again you'll predict a maximum, and it's then just the instability that will lead to the neck forming. In terms of, if your question is related towards porosity and voids in additively manufactured materials, certainly they can act to promote fracture prematurely, so maybe earlier in the necking, once the material has necked, or maybe even before necking, and that is something that we can't capture with indentation. The stresses in general are compressive, and therefore we're not stimulating any fracture during the indent. But there is no consideration of voids in the simulation, because actually you predict the neck without any voids. That's just a continuum.
Okay. Thank you, sir. Thank you very much.
Yeah. Thank you, Rupam. Any other questions from the audience? So, Dr. Jimmy, you have shown one video that so I wanted to know what should be the sample roughness do you expect?
So what sort of roughness is acceptable? Is that the question?
Sorry, are you asking what kind of surface preparation is needed?
Yeah.
I mean, the answer to that is that it doesn't need to be highly polished or anything. I mean, one of the big advantages of doing this on a relatively coarse scale is that it's not very sensitive to surface roughness. Of course, if it's very rough, if you have a thick oxide layer on the surface, or you have very, very deep grooves or something, then it might create an error. But generally speaking, you just need to grind this to a reasonable finish. You don't even need to polish it, and if you do polish it, you certainly don't need to polish it very finely.
Yeah, so we typically recommend that a grind of P1200 grit is appropriate. That's more than enough. So we don't suffer, like Bill said, the problems that you might associate with nano indentation, where you do need a very good finish to make sure that that's not going to affect the response of the material, because you're indenting on such a fine scale. So yeah, the requirements for surface finish are actually not too demanding.
Okay.
I mean, there is one point you might like to note there, which is that if you do get a reasonable finish, you might see some interesting things. Like here, for example. Now that's just the free surface there around the indent, and it was well polished beforehand. And you start to see some interesting things that look like these persistent slip bands, where lots of dislocations have followed each other and reached the free surface. In fact, if you look carefully, you can see other things. You can see deformation twins or prior annealing twins, and you also see grain rotations. So this kind of thing becomes clearer if you have created a polished surface to start with. But in terms of actually doing the test, you don't need a polished surface.
Right. Okay. Can you go to your residual stress slide? Just I wanted to say one detail. So there, here, what you are doing is you are stretching the samples from both sides, right?
Yeah.
and then you are doing the in situ indentation.
Yeah.
Okay. Okay. Thank you. Yeah. So any other questions from audience before? Yeah. So if there is no more questions from the audience, let us thank Professor Clyne and Dr. Jimmy for the very valuable talk, and they have shared that very innovative technique for measuring the mechanical properties of a material. Thank you so much. Thank you so much, Professor Clyne and Dr. Jimmy. Thank you so much.
Thank you, Ajay.
Yeah.